In this lesson, we will learn about truss, determine the force in members of a simple truss, and identify zero force members. So what is a truss? A truss is a structure composed of slender members joined together at their end points. If a truss, along with the imposed load, lies in a single plane, then it is called a planar truss. A simple truss is a planar truss which begins with a triangular element and can be expanded by adding two members and a joint. For these trusses, the number of members m and the number of joints j are related by this equation. When designing both the member and the joint of a truss, first it is necessary to determine the forces in each truss member. This is called force analysis of a truss. When doing this, two assumptions are made. All loads are applied at the joints. The weight of a truss member is often neglected as it is usually small as compared to the forces supported by the truss members. The members are joined together by smooth pins. This assumption is satisfied in most practical cases where the joints are formed by bolting the ends together. With these two assumptions, the members act as two-force members. They are loaded in either tension or compression. Often compressive members are made thicker to prevent buckling. When using the method of joints to solve for the forces in truss members, the equilibrium of a joint pin is considered. All forces acting at the joint are shown in a free body diagram. This includes all the external forces, including support reactions, as well as the forces acting in the members. Equations of equilibrium are used to solve the unknown forces acting at the joints. Here are the following steps for truss analysis. If the truss's support reactions are not given, draw a free body diagram of the entire truss and determine the support reactions, typically using scalar equations of equilibrium. Draw the free body diagram of a joint with one or two unknowns. Assume that all unknown members' forces act in tension, unless you can determine by inspection that the forces are compression loads. Apply the scalar equations of equilibrium in the x and y direction to determine the unknowns. If the answer is positive, then the assumed direction, tension, is correct. Otherwise, it is in the opposite direction, such as compression. Repeat step 2 and 3 at each joint in succession until the required forces are determined. If a joint has only two non-collinear members and there is no external load or support reaction at that joint, then those two members are zero force members. In this example, members DE, DC, AF, and AB are zero force members. You can easily prove these results by applying the equations of equilibrium at joint D and A. Zero force members can be removed, as shown in this figure, when analyzing the truss problem. If three members form a truss joint for which two of the members are collinear and there is no external load or reaction at that point, then the third non-collinear member is a zero force member. Again, this can easily be proven. One can also remove the zero force member for analyzing the truss further. Please note that the zero force members are used to increase stability and rigidity and to provide support for various loading conditions. In this example, a load is applied as shown at point D, and the force in each member of the truss has to be determined. Check if there are any zero force members. First analyze pin D and then pin A. Note that member BD is a zero force member. So the free body diagram at point D is shown here. Now applying the equation of equilibrium in the x direction, repeating in the y direction, we get two equations and two unknowns. Solving these two equations simultaneously, we obtained force in the CD member 318 pounds in tension. Similarly, in the member AD, which is minus 318 pounds, meaning that it is compression force. Now, to determine forces in the member AB or BC, we need to draw a free body diagram at point A and apply the equation of equilibrium. This results force in the member AB equal to 225 pounds, which is in tension, and it is the same as that is in the member BC, which is also in tension. Thanks for watching.